All right, welcome back. We are here with MOGAS, and we have a 24-inch delayed coker isolation valve, their so-called C-Series valve, for this particular shop floor interview, and we've brought in Michael Birkenhoff. Sorry, Michael. We're going to talk about some specific aspects of their C-Series valve, and I'd like to bring your attention first to the purge port. So this is a little bit different than some of the other layouts that you might be familiar with. There are 3 purge ports on the system. There's one for the body, one for the seat, and one for the Vortex. So I'll allow Michael to just sort of introduce what these are and how they work.
Sure, so we call it our Vortex Purge, and it is actually a patented purge process. One of the things you'll notice is it is on an angle. So it's not just going straight into the valve like a typical purge would. And that is not by design or that is by design, it's not by accident. That is actually something that the engineering team spent a lot of time and effort into developing. It was first studied with CFD analysis and later backed up with some actual testing. And what was found is that if you angle the purge and you send it around, you actually are wrapping it around rather than just pushing it in one spot. And all 3 of these purges work together. There's no just one purge. So you'll see there's a 3rd purge on the other side. For demonstration purposes, you see we have the boss and the casting. The purges can be put from either side. It's just a customer application, but you can get the sense of it that when the purge fluid's coming in, along with the purge fluid from that Vortex purge on the other side, it does create this swirling motion inside, which suspends the fluids, which suspends any sediment that is in the valve. And ultimately, you can come out with a drain. You'll see we have a boss there. This is something MOGAS would recommend. You can hook up into a drain, which you would use just before and after cycling the valve. You would not keep that open all the time. You'd be losing steam at that point. But even if you don't run it with a drain configuration, it still suspends the solids significantly better than it would if you just had a purge coming straight into it like in a conventional arrangement.
So you have this, I think it's obvious right away, to state the obvious, this is the valve laying on its side. It would be upright 90 degrees. This swirling action is created by this tangential motion, but you'll notice that there's only one seat purge on here, and I think that's a little bit unique. So how does that seat purge get into this cleanliness of the valve?
Right, so the seat purge is coming in behind the seat, and it's trapped in between the seat and the spring. And one thing we do differently as well is we use a Belleville spring, which if you're not familiar with it, you maybe hear called a Belleville washer, but it's a 1-piece spring arrangement, and this is for a 12-inch valve, so obviously it'll be much bigger as the valve gets larger. But it is essentially a single piece of metal that is formed on an angle. So the advantage of this type of spring, and it is a spring, but you get a very high K factor. So for a small amount of vertical displacement, you get a large force out of it. So what that's doing is that's pushing the ball and seat into each other, pushing the seat into the ball. And that's going to keep it clean between the seat and ball. It's also going to keep it clean between the spring and the valve body. And so that is where we keep the particles out of that spring cavity. And when you do put the purge behind the Belleville spring, the one purge that we talk about, it's not even just a blowing purge, it's really just more like a clean room purge where it's keeping it at a higher pressure. And that is why there is not a large steam consumption with that type of arrangement.
Very interesting. And I think this is something that this very large spring force in combination with that seat purge, because we all know these valves live or die by their steam supply to keep them healthy over the long run. This is sort of like a belt and suspenders sort of approach to how you want to maintain that ball seat surface as long as possible, right?
That's correct. So the other thing that does is by putting that high force behind it, the seat pushing into the ball, and along with the MOGAS design of a sharper edge on that, is when the two do cycle against each other. So when you do cycle the valve, it does cut away any particles that it's trying to collect onto that ball to seat arrangement. And that also contributes to keeping the system clean and keeping it performing well for years to come.
And that particle, that scraping motion is something that you've demonstrated over years of operation in emulated bed, heavy oil services, as well as the delay coker service.
That's correct. We've got a long history in nebulated bed, heavy oil service, and also the delay coker valves that we've had out there now for the past several years have all been performing and demonstrating that it does not build up on that surface.
Interesting. Well, thank you very much, Mike, for sharing your insights about the design of the MOGAS valve, this very large beast of a valve that we know and love in the delay coker industry. So if you'd like to learn more from folks like Mike, come to RefComm, come to our conference. You'll learn a lot from these guys and everyone else that'll be at the event. So thank you for your time.
Thank you.
And we look forward to more vendor spotlights in the future. Thank you.